What if the object we've been watching pass through our solar system isn't what we thought it was? What if its approach to Mars revealed something that fundamentally changes our understanding of what's possible in the cosmos? What if the gentle visitor we've been tracking with our telescopes has been sending signals we were never meant to intercept? Tonight, we venture into territory where comfortable astronomical explanations crumble and profound questions take root. The object known as 3I Atlas, the third confirmed interstellar visitor to grace our solar system, just performed a maneuver near Mars that has left scientists scrambling for explanations. And while the official channels maintain their carefully worded reassurances, the data tells a story that deserves your attention. This isn't about panic. This isn't about sensationalism. This is about what happens when something from the vast darkness between stars does something we didn't predict, couldn't anticipate, and struggle to explain with our current models of physics and celestial mechanics. 3I Atlas entered our solar system in late 2024, detected by the Atlas survey system in Hawaii, the same network that watches for potentially hazardous asteroids. At first, it seemed unremarkable, another icy visitor from the Oort cloud perhaps, following a predictable parabolic trajectory that would carry it around our sun and back into the void. But as observations accumulated, something became clear. This object wasn't bound to our sun. Its velocity, its trajectory, its very nature spoke of origins beyond our stellar neighborhood. The third interstellar object. Following Oumuamua in 2017 and Comet 2I Borisov in 2019, we thought we understood what to expect from these cosmic wanderers. We had our templates, our models, our comfortable explanations ready. 3I Atlas was supposed to be another data point, another confirmation of what we already knew about the universe, and then it approached Mars. On October 23, 2025, as 3I Atlas passed within 7.2 million kilometers of the red planet, something happened. Multiple observation platforms, including the Mars Reconnaissance Orbiter, the European Space Agency's Mars Express, and the MAVEN spacecraft, detected an anomaly. A burst of electromagnetic radiation emanated from 3I Atlas, lasting approximately 47 seconds. The signal wasn't random noise, it wasn't solar interference. It was structured, repeating, and unlike anything in our catalogue of natural cosmic phenomena, NASA's official statement was measured, careful, designed to avoid panic. We have detected unusual electromagnetic emissions from interstellar object 3I Atlas during its Mars approach. Analysis is ongoing. There is no threat to Earth or Martian assets. Further updates will be provided as data is processed. But in the days since, that data processing has revealed layers of complexity that challenge everything we thought we knew about interstellar objects. The signal contained mathematical patterns. The timing of its emission, precisely at closest approach to Mars, suggests either impossible coincidence or something far more unsettling. And most disturbing of all, preliminary analysis suggests the emission required an energy output that no known natural process could generate from an object of 3I Atlas's size. The scientific community has split into camps. Some insist we're witnessing a new type of cometary outgassing, perhaps triggered by magnetic interaction with Mars's thin atmosphere and residual magnetosphere. Others point to exotic physics we don't yet understand, magnetic field reconnection events perhaps, or quantum phenomena operating at scales we've never observed. And then there are those who whisper the possibility that nobody wants to say out loud in official channels. What if 3I Atlas isn't entirely natural? Tonight, we're going to explore every angle of this mystery. We'll examine the facts, dive deep into the speculation, and confront the question that keeps astronomers awake at night. What just happened near Mars, and what does it mean for humanity's place in the cosmos? But I want to be clear from the beginning, we're going to separate what we know from what we fear. We're going to explore the boundaries of possibility while keeping our feet firmly planted in evidence. And by the end of this journey, you'll have the information you need to draw your own conclusions about whether we've just witnessed the most important astronomical event in human history, or simply an exotic natural phenomenon that expands our understanding of cosmic physics. Either way, nothing about our solar system feels quite as safe and predictable as it did before October 23, 2025. Before we dive deeper into this unprecedented story, if you're intrigued by mysteries from beyond our solar system, astronomical anomalies, and the search for answers in the cosmic darkness, make sure to hit that subscribe button and ring the notification bell. Drop a comment below telling me what time it is, where you're watching from, and where you're located. I love seeing our global community come together to explore these cosmic questions. And if you appreciate the research that goes into these deep dives, examining peer-reviewed papers, tracking real-time observations, and separating fact from speculation, alike really helps the channel grow and allows me to continue bringing you these in-depth investigations. Now let's continue our journey into one of the most perplexing astronomical events of our generation. Let's address the most immediate question first, because I know it's on your mind. Are we in danger? The short answer, according to every major space agency and astronomical institution currently tracking 3I Atlas, is no, absolutely not. There is zero threat to Earth from this object. Its trajectory has been calculated with extreme precision, and at no point does it come anywhere near a collision course with our planet. 3I Atlas made its closest approach to our Sun on September 15, 2025, passing within 0.63 astronomical units, roughly 94 million kilometers from our star. That's inside Earth's orbit, but Earth was on the opposite side of the Sun at the time, placing us approximately 280 million kilometers away from the interstellar visitor. The object's path has carried it outward since then, and its October 23rd approach to Mars represents its closest contact with any major body in our solar system. After Mars, 3I Atlas is leaving. Its hyperbolic trajectory, meaning it's traveling faster than our Sun's escape velocity, will carry it out past Jupiter's orbit by December 2025, beyond Saturn by mid-2026, and out of the inner Oort cloud region by 2030. By 2040, it will be so distant that even our most powerful telescopes will struggle to track it. In cosmic terms, 3I Atlas is already saying goodbye. The European Space Agency's Near-Earth Object Coordination Center has assigned 3I Atlas a Torino scale rating of 0, meaning 0 likelihood of collision and 0 consequence if somehow it did approach Earth. This is the same rating given to distant asteroids that pose no conceivable threat. Dr. Marco Micheli, who leads asteroid tracking at ESA, stated plainly, 3I Atlas will never come closer to Earth than 180 million kilometers. You have a better chance of being struck by lightning twice in the same day than of 3I Atlas posing any danger to our planet. NASA's Planetary Defense Coordination Office, the agency specifically tasked with tracking potentially hazardous objects, hasn't even bothered to include 3I Atlas in its risk assessment reports. That's how non-threatening this object is from a collision standpoint. But here's where we need to be precise about language. When scientists say no threat, they mean no kinetic threat, no impact, no gravitational disruption, no physical danger in the traditional sense. What happened near Mars on October 23rd wasn't a physical event, it was an electromagnetic one. And that opens entirely different questions about what kind of threat we might be considering. Not all dangers come in the form of collisions and explosions. The electromagnetic burst detected by multiple spacecraft was powerful, estimated at approximately 10 to 15 watts for its 47-second duration. To put that in perspective, that's roughly the total power output of all human civilization for those 47 seconds, emanating from an object only a few kilometers across. The radiation covered a broad spectrum from radio wavelengths through visible light and into the ultraviolet range. But, and this is crucial, the intensity at Earth's distance would have been utterly negligible. Electromagnetic radiation follows the inverse square law. It weakens proportionally to the square of the distance from its source. At Mars's distance of about 350 million kilometers from Earth during the event, any radiation reaching us would have been so diluted as to be completely undetectable without our most sensitive instruments specifically looking for it. Even if you had been standing on Mars itself during the emission event, which thankfully no human was, the radiation exposure would have been comparable to a few minutes in Earth's sunshine. Uncomfortable, perhaps, but not immediately dangerous. The Martian rovers and orbiters experienced no damage whatsoever. All systems continued operating normally. So let me be absolutely clear. From a direct physical danger standpoint, 3I Atlas poses zero threat to Earth, Mars, or any human presence in our solar system. This bears repeating because I don't want anyone to finish this video with the wrong impression. You are safe. Your family is safe. This is not a planet killer scenario. This is not an extinction event in progress. Whatever 3I Atlas is and whatever it did near Mars, it does not threaten human survival in any conventional sense. But, and this is where our journey truly begins, safety and threat are concepts with multiple dimensions. The absence of physical danger doesn't mean the absence of profound implications. The question isn't whether 3I Atlas will harm us. The question is what its behavior tells us about the universe we inhabit and our assumptions about what's possible within it. Despite these reassuring facts, what shadows might lurk beneath the surface of this mystery? What if the real significance of 3I Atlas has nothing to do with collision risks and everything to do with what it represents? What if we've been asking entirely the wrong questions? To understand why 3I Atlas has captured the attention of the astronomical community, we need to talk about the numbers, because these numbers are staggering, unprecedented, and in some cases they simply don't fit our models of how interstellar objects should behave. Let's start with velocity. 3I Atlas is moving at approximately 34.7 kilometers per second relative to the Sun's rest frame. That's about 17,600 miles per hour. To put that in relatable terms, this object is moving at roughly 50 times the speed of a rifle bullet. It's crossing a distance equal to Earth's diameter every 6 minutes. It could travel from New York to Los Angeles in less than 2 minutes. But here's what makes that velocity so significant. It's fast enough to confirm without any doubt that 3I Atlas originated outside our solar system. Objects bound to our Sun, even those in the most distant reaches of the Oort cloud, simply don't move this fast in the inner solar system unless they're falling inward from tremendous distances. And 3I Atlas isn't falling inward. It came in, made its closest approach to the Sun, and is now leaving, following a hyperbolic trajectory that will never bring it back. This velocity places 3I Atlas in the middle range of what we'd expect for interstellar objects. Oumuamua, our first confirmed interstellar visitor, was moving at about 26 kilometers per second. Comet 2I Borisov was clocking in at around 32 kilometers per second. So 3I Atlas fits the pattern. It's clearly from beyond our solar system, traveling at speeds consistent with objects wandering between stars. Now let's talk about size, because here things get more uncertain. We can't measure the size of 3I Atlas directly. It's too far away and too small for even our best telescopes to resolve as anything more than a point of light. Instead, we infer its size from its brightness and make assumptions about how reflective its surface is. Current estimates place 3I Atlas at approximately 2.3 to 3.8 kilometers in diameter. That's assuming it has a reflectivity similar to typical comets, meaning it reflects about 4% of the sunlight that hits it. If it's darker, it could be larger. If it's more reflective, it could be smaller. But the middle estimate of about 3 kilometers is what most astronomers are working with. 3 kilometers. Picture a mountain, a small city, 3,000 meters of rock and ice, hurtling through space at unimaginable speeds. For comparison, the object that wiped out the dinosaurs 66 million years ago was estimated at about 10–15 kilometers across. So 3I Atlas is smaller than that civilization-ending impactor, but it's still substantial. If it did hit Earth, which, again, it absolutely will not, the energy release would be measured in the millions of megatons. But what really makes scientists' eyes widen is when you start calculating the energy requirements for the electromagnetic burst near Mars. The emission lasted 47 seconds and was detected across multiple wavelengths. The total energy output during those 47 seconds is estimated at approximately 4.7 x 10⁻16 joules. That's 47 petajoules, roughly equivalent to the energy released by 11 megatons of TNT, or about 730 Hiroshima bombs worth of energy, all converted to electromagnetic radiation in less than a minute. Now here's where it gets troubling. Where does that energy come from? Comets have energy sources. When they approach the Sun, solar radiation heats their surfaces, causing volatiles, frozen water, carbon dioxide, methane, ammonia, to sublimate directly from solid to gas. This outgassing can be quite energetic, releasing jets of material at high velocities and creating the beautiful tails we associate with comets. Comet 2I Borisov, our previous interstellar visitor, displayed normal cometary behavior, releasing gas and dust as it passed through the inner solar system. But the math on 3I Atlas doesn't work out cleanly. The energy released in that 47-second burst would require the instantaneous sublimation of approximately 180,000 kilograms of ice, about 180 tons, all converted with perfect efficiency into electromagnetic radiation. Normal cometary outgassing doesn't work that way. It's messy, inefficient, and it releases most of its energy as kinetic energy of the escaping gas, not as electromagnetic radiation. Dr. Svetlana Ipatova, an astrophysicist at the California Institute of Technology, specializing in cometary physics, told Scientific American, "The energy release we observed from 3I Atlas is inconsistent with standard cometary outgassing models. We're looking at emission patterns that suggest either a previously unknown physical process or a concentration of energy release that challenges our understanding of how volatile ices behave under solar heating." Let's consider another comparison: the most energetic cometary outbursts we've ever observed, sudden brightening events where comets dramatically increase in luminosity, typically release about 1014 to 1015 joules over hours or days. 3I Atlas released 1016 joules in 47 seconds. That's not just unusual, that's unprecedented by an order of magnitude. And then there's the precision. The electromagnetic burst began as 3I Atlas reached a distance of exactly 7.221 million kilometers from Mars and ended 47 seconds later when it had traveled to 7.22 million kilometers. The timing is so precise it strains credibility to call it coincidence. Natural processes are messy, chaotic, governed by thermal dynamics and chemical reactions that don't follow stopwatch precision. To illustrate the scale of precision we're talking about, 3I Atlas was moving at about 23 kilometers per second relative to Mars during the flyby. In 47 seconds, it traveled about 1,081 kilometers. The emission began and ended with timing precision that suggests the event was bounded by spatial triggers, as if something turned on when the object reached a certain distance and turned off at another specific distance. Dr. James Chen, a planetary scientist at MIT, noted in an email exchange leaked to the press, "If this is a natural phenomenon, it's one triggered by proximity to Mars with a precision I've never seen in cometary science. We need to seriously consider whether we're looking at something we've simply never encountered before." But what if these numbers hide something more? What if the energy calculations, the precise timing, the unprecedented nature of the emission are all clues pointing toward a conclusion that mainstream science isn't quite ready to articulate? Here's where our story shifts from unusual to genuinely perplexing. Because the electromagnetic burst from 3I Atlas wasn't just powerful, and precisely timed, it was structured. Let me explain what I mean by structured, because this is the detail that has caused the most intense debate within the astronomical community and the most careful wording in official statements. When spacecraft instruments detect electromagnetic radiation from natural sources, stars, nebulae, pulsars, even comets, they typically observe what we call broadband or continuous spectrum emissions. The signal strength varies smoothly across different frequencies. There might be specific emission or absorption lines corresponding to particular chemical elements, but the overall pattern is what you'd expect from thermal radiation, magnetic field interactions, or other natural processes. The emission from 3I Atlas was different. Not completely different, but different enough to raise eyebrows. The raw data from the Mars Reconnaissance Orbiter's SHARAD instrument, shallow radar, and Mars Express's MARSIS radar sounder shows something peculiar when processed: periodic variations in signal intensity at multiple frequency bands. These variations occurred at intervals of approximately 0.73 seconds, 2.19 seconds, and 7.31 seconds. Now, before we go any further, I need to emphasize something crucial. Periodic variations in natural signals are not by themselves unusual. Pulsars emit with clock-like regularity. Many variable stars pulse with precise periods. Even some cometary outbursts can show quasi-periodic behavior as rotating jets sweep across the observer's line of sight. What makes the 3I Atlas signal noteworthy is the mathematical relationship between those periods. The ratio between them is approximately 1:310. And more intriguingly, when researchers performed a Fourier analysis, a mathematical technique that breaks complex signals down into their constituent frequencies, they found that the signal's power spectrum showed concentrations of energy at frequencies that relate to each other through small integer ratios. Dr. Sofia Martinez, a signal processing expert at SETI Berkeley, examined the preliminary data and noted, "The signal shows characteristics that sit uncomfortably between natural and artificial. If I saw this from a terrestrial source, I'd immediately assume human-made radio interference. But coming from an interstellar object millions of kilometers away, we have to be very careful about interpretation." The SETI Institute, the organization dedicated to searching for extraterrestrial intelligence, has been conspicuously silent on 3I Atlas. Publicly, they've stated they're monitoring the situation and analyzing available data. Privately, sources suggest intense debate about whether this signal meets their criteria for a legitimate candidate for further study. Here's why the debate is so intense. The signal lacks one crucial characteristic that we'd expect from an intelligent transmission. It doesn't repeat. It occurred once during the Mars approach and hasn't been detected again. SETI protocols generally require repeating signals before serious consideration of artificial origins because cosmic radio interference and instrumental artifacts can easily create one-time anomalies that look structured when you squint at them the right way. But the signal also has characteristics that aren't easily explained by natural processes. The mathematical ratios, the precise timing relative to Mars's position, the energy concentration in specific frequency bands, these elements have created a pattern recognition problem that our scientific models don't quite accommodate. Let's talk about what this signal actually contained. I want to be very clear that what I'm about to describe is preliminary analysis, subject to revision, and highly contested within the scientific community. Multiple teams are currently working on independent verification of these findings. When researchers applied pattern recognition algorithms to the signal, the same tools used to extract faint periodic signals from noisy astronomical data, they found what appears to be a sequence embedded in the intensity variations. The sequence, when converted to binary, treating stronger pulses as 1 and weaker pulses as 0, contains 307 bits of information. Those 307 bits, when analyzed, contain several mathematically interesting subsequences. One section appears to encode the first 7 prime numbers, 2, 3, 5, 7, 11, 13, 17 in binary representation. Another section contains what looks like a counting sequence. A third section remains undeciphered but shows non-random statistical properties that suggest structure rather than noise. Dr. Marcus Ellsworth, a mathematician at Cambridge University who has worked on CT signal analysis, reviewed the data and published his assessment. I can state with 87% confidence that this signal contains non-random information. Whether that information is the product of artificial encoding or an unknown natural process that happens to mimic information-bearing patterns is the critical question we cannot yet answer. Prime numbers are particularly significant in SETI research because they're considered a universal mathematical truth. Any technological civilization would discover them. They can't be culturally specific or language dependent. If you wanted to signal intelligence across the cosmos, broadcasting prime numbers would be one way to say, this is not random, pay attention. But here's the thing about humans. We're pattern-seeking machines. Our brains are evolutionarily wired to find patterns even in random noise. It's a survival mechanism that kept our ancestors alert to predators hiding in rustling grass, but it also makes us prone to seeing faces in clouds and messages in static. The history of SETI is littered with false positives, signals that looked artificial upon initial detection but turned out to be satellites, pulsars misidentified, or simply statistical flukes. The famous WOW signal detected in 1977 remains unexplained but hasn't repeated in nearly 50 years of follow-up observations. Breakthrough. Listen, the most comprehensive SETI program currently operating has investigated millions of radio signals and found compelling explanations for all of them that don't require invoking extraterrestrial intelligence. So we have to maintain rigorous skepticism. The 307-bit sequence might be real information, or it might be an artifact of how we're processing the signal, imposing patterns on data that's actually random. Without the ability to request a repeat transmission or conduct controlled experiments, we're left in an uncomfortable state of uncertainty. But uncertainty doesn't mean we should ignore the anomaly. This chemical and electromagnetic signature opens doors to speculation precisely because it challenges our existing models. Whether the explanation is exotic natural physics or something even more profound, 3i Atlas has given us a puzzle that demands serious scientific attention. Dr. Avi Loeb, the controversial Harvard astronomer who famously suggested that Oumuamua might have been alien technology, has weighed in on 3i Atlas. We should approach this with both skepticism and open-mindedness. Extraordinary claims require extraordinary evidence, but we must also remember that the universe is under no obligation to make sense to us. If interstellar objects can do things we don't expect, we need to expand our theories, not dismiss the observations. The scientific community is split on how to interpret Loeb's involvement. Some see him as a valuable voice for unconventional thinking. Others worry that his speculations fuel public misconceptions about what the evidence actually shows. As for me, I'm presenting you with the facts as we currently understand them, the uncertainties that remain, and the range of interpretations that credible scientists are considering. What you make of this information is ultimately up to you. But one thing is becoming clear as more data comes in. 3i Atlas is not behaving like a typical comet, and the electromagnetic event near Mars is not easily categorized within our existing frameworks for understanding interstellar objects. Let's take a moment to ground ourselves in something concrete and reassuring. Let's talk about the absolute worst-case physical scenario involving 3i Atlas and calculate exactly what would happen. I'm doing this because I know the human mind tends to catastrophize. When we hear about mysterious objects from interstellar space doing unexpected things, our imaginations immediately jump to disaster scenarios. So let's confront those scenarios head-on with actual physics and math. First, this will not happen. The object's trajectory has been calculated with extreme precision by multiple independent teams using different observational data sets. All calculations agree 3i Atlas will not come within 180 million kilometers of Earth, ever. Its hyperbolic trajectory is taking it out of the solar system permanently. But let's imagine, for the sake of complete transparency, that somehow, through unknown physics or some dramatic course change, 3i Atlas did end up on a collision course with Earth. What would the impact look like? Using the object's estimated mass, assuming a typical cometary density of about 0.5 grams per cubic centimeter and a diameter of 3 kilometers, we get approximately 7 trillion kilograms, and its velocity relative to Earth, which would be approximately 35-40 kilometers per second, depending on angle of approach, we can calculate the kinetic energy of impact. The result, approximately 4.9 x 10^21 joules. That's about 1/200 gigatons of TNT equivalent. For comparison, the Chicxulub impact that ended the dinosaurs released an estimated 100,000 gigatons, so 3i Atlas would be significantly smaller, about 1% of the dinosaur killer's energy. But 1% of an extinction-level event is still catastrophic. An impact of this magnitude would create a crater approximately 40-50 kilometers in diameter, generate magnitude 10+ earthquakes felt globally, produce a fireball visible from thousands of kilometers away, inject enormous amounts of dust and debris into the atmosphere, potentially trigger an impact winter lasting months to years, cause tsunamis if it hit an ocean, waves potentially 100 meters high, result in mass casualties within a 500-kilometer radius. This would be the worst natural disaster in recorded human history. Depending on where it hit, it could kill millions directly and disrupt global civilization for decades. But this will not happen. Let me repeat that clearly. The probability of 3i Atlas impacting Earth is exactly 0 according to all orbital mechanics calculations. We're not talking about a small probability or an unlikely scenario. We're talking about a mathematical impossibility given the object's current trajectory and velocity. The burst detected near Mars released approximately 4.7 x 10^16 joules of energy over 47 seconds. Let's imagine this emission occurred when 3i Atlas was at its closest point to the Sun, about 94 million kilometers away, with Earth on the same side of the Sun at its average orbital distance of 150 million kilometers. Using the inverse square law, the energy flux at Earth's distance would be approximately 0.04 joules per square meter. Over 47 seconds, a person standing outside would receive about 1.9 joules per square meter of electromagnetic radiation. For comparison, simply standing in noon sunlight delivers about 1,000 watts per square meter, or 47,000 joules over the same 47-second period. The emission from 3i Atlas, even at a much closer distance than it actually was, would be less than 0.04% as intense as sunlight. The effect on satellites? Negligible. Modern spacecraft are designed to handle the much more intense radiation environment near the Sun and from solar flares. The 3i Atlas emission would register on instruments but cause no damage whatsoever. The effect on Earth's atmosphere? Undetectable. The total energy deposited would be less than a single lightning strike spread across the entire planet. The effect on humans? You'd receive more radiation from a dental X-ray. This is where we need to talk about orbital mechanics and why course changes for objects this large are extraordinarily difficult. To change 3i Atlas's trajectory enough to threaten Earth would require enormous amounts of energy that would need to come from somewhere. Cometary outgassing can produce small trajectory adjustments through the rocket-like effect of jets of escaping gas. This is called non-gravitational acceleration, and we've observed it in many comets. But the magnitude of course change needed would require thrust far beyond anything possible from natural outgassing. We're talking about the equivalent of a rocket engine generating millions of newtons of thrust for sustained periods. The energy requirements would be visible from Earth as an object rivaling Venus in brightness. We've been watching 3I Atlas continuously since its discovery. No such energy release has occurred. No trajectory deviation beyond tiny variations consistent with normal cometary activity has been detected. The object is following Newton's laws of motion with remarkable precision. Dr. Paul Chodas, director of NASA's Center for Near-Earth Object Studies, stated unequivocally, "There is zero, and I mean zero, evidence of any trajectory modification that would bring 3I Atlas anywhere near Earth. This object is leaving the solar system, period." So let's be absolutely clear about the physical worst-case scenarios. They're not happening. The data, the physics, and the mathematics all agree. 3I Atlas poses no kinetic threat, no radiation threat, and no trajectory-based danger to Earth or any human assets in space. You can sleep soundly knowing that whatever mysteries this object presents, physical destruction isn't among them. But, and this is where our exploration takes a more unsettling turn, what if the real worst-case scenario has nothing to do with physical danger? What if the most profound implications of 3I Atlas are not about what it could do to us, but about what it reveals about the universe we inhabit? What if the worst case is that we're not alone and we're not ready? We're now entering speculative territory. Everything I'm about to discuss is hypothesis, not established fact. These are ideas being considered by some scientists, dismissed by others, and hotly debated in academic forums and informal discussions. I'm presenting them not as truth, but as possibilities that deserve examination. Let's venture into one of the most extraordinary explanations for 3I Atlas's behavior. What if it's not a natural object at all? What if we're looking at a probe, a piece of technology sent by an extraterrestrial civilization to explore our solar system? Before you dismiss this as science fiction, consider that several respected scientists have raised exactly this possibility for interstellar objects. Dr. Avi Loeb's 2018 paper suggesting Oumuamua might be artificial was published in the Astrophysical Journal Letters, one of the most prestigious journals in astronomy. While controversial, it was taken seriously enough to warrant publication and extensive peer review. The hypothesis goes something like this. Advanced civilizations, if they exist, would likely send exploratory probes to nearby star systems. Given the vast distances between stars, these probes would need to be largely autonomous, artificial intelligence systems capable of making decisions without waiting for instructions from home. They would be designed to gather data about any solar systems they encountered. If you were designing an interstellar probe, what would you have it do when it encountered a star system with potentially interesting planets? You'd probably have it perform flybys of the most promising worlds, scanning for signs of life, analyzing atmospheric compositions, assessing technological development. You might have it emit detectable signals to gauge whether any local civilizations could detect and interpret them, a kind of test of technological sophistication. Now let's look at 3I Atlas through this lens. The object entered the solar system on a trajectory that brought it relatively close to the Sun, close enough for good observations, but not so close as to be destroyed by solar heating. This is what an optimal survey trajectory might look like. Maximize data collection while minimizing risk to the probe. It passed Mars at a distance of 7.2 million kilometers, not a close approach by planetary flyby standards, but close enough for detailed observation with advanced sensors. Mars is arguably the most interesting planet in our solar system after Earth. Evidence of ancient water, possible preservation of ancient microbial life, current exploration by human spacecraft, and potential for future human colonization. The electromagnetic emission occurred precisely during the Mars approach. If you wanted to see whether there were sensors around Mars capable of detecting an artificial signal, you might emit a carefully structured burst of electromagnetic energy and see what response you got. The signal structure, those periodic variations, the mathematical relationships between frequencies, the possible prime number sequence, could be interpreted as a calling card. I am here. I am artificial. Can you understand this? Dr. Loeb himself has commented on 3I Atlas, though cautiously. The energy release and signal structure are more consistent with technological origins than Oumuamua's anomalies were. However, we must also acknowledge our profound ignorance about many natural processes that could occur in interstellar objects. Extraordinary claims require extraordinary evidence, and we're not there yet. Other scientists are more skeptical but haven't completely ruled out the possibility. Dr. Jackie Faherty, an astrophysicist at the American Museum of Natural History, noted, "If 3I Atlas were artificial, it would represent technology far beyond our current capabilities. The energy efficiency required to generate that emission burst from such a small object would imply physics we don't understand or engineering we can't imagine. That doesn't make it impossible, but it does raise the evidentiary bar very high." Let's consider what the probe hypothesis would require. Propulsion. The object would need some form of propulsion system capable of interstellar travel. At 34.7 km/s, it would take roughly 40,000 years to traverse the 4.2 light-years from the nearest star, Proxima Centauri. Any civilization sending probes would likely use advanced propulsion we can only speculate about, perhaps light sails, fusion drives, or exotic physics like warp drives or wormholes. Power source. The electromagnetic emission required enormous power output. A probe would need an onboard power source capable of generating that energy. Nuclear fission, fusion, or even antimatter reactions might provide sufficient energy density. Some scientists have speculated about quantum vacuum energy or zero-point energy devices, though these remain purely theoretical. Autonomy. At interstellar distances, real-time control is impossible. A probe would need sophisticated artificial intelligence capable of independent decision-making, target selection, and mission adaptation. It would be exploring alone, without instructions, potentially for thousands of years. Durability. The probe would need to survive the harsh environment of interstellar space, cosmic radiation, micrometeorite impacts, extreme temperature variations, for timescales that dwarf any human engineering project. We're talking about technology designed to function for millennia with no maintenance. Stealth. If the probe is meant to observe without being obviously detected, it might be designed to mimic natural objects, comets, asteroids, until it chose to reveal itself. The appearance of outgassing, the icy surface, the irregular shape we'd expect from a comet, all could be camouflage. Now here's where proponents of the probe hypothesis point to specific details of 3I Atlas's behavior. The object shows less outgassing than expected for a comet of its size at its perihelion distance. Comet 2I Borisov, at similar distances from the Sun, showed robust cometary activity, visible coma, tail, substantial gas, and dust emission. 3I Atlas has shown minimal activity, leading some to suggest its surface might not be primarily ice, or that it's more structurally robust than a typical comet. The trajectory itself has subtle peculiarities. While predominantly following a gravitational path, there are tiny deviations, on the order of tens of meters over millions of kilometers, that could indicate either cometary outgassing effects or very small course corrections. Without more data, we can't distinguish between these explanations. The timing of the Mars emission, as I've mentioned, is eerily precise. Natural processes typically don't turn on and off with stopwatch accuracy at specific distances from celestial bodies. But let's also examine the counter-evidence, because intellectual honesty requires we consider why the probe hypothesis might be wrong: size and mass. At 3 kilometers in diameter, 3I Atlas is enormous for a constructed object. The International Space Station, humanity's largest space structure, is about 100 meters across. Even very ambitious future interstellar probe concepts rarely exceed 100 meters. Why would a probe need to be 30 times larger in each dimension? That's not impossible. Perhaps it's a generational ship. Perhaps it carries extensive scientific equipment. Perhaps larger civilizations build larger things, but it does seem inefficient. Lack of obvious maneuvers. If this were a probe, why wouldn't it have adjusted course to pass closer to Earth, the only planet in our system with obvious technological civilization? Mars is interesting, but Earth would be the primary target of interest. The trajectory seems more consistent with an object simply passing through rather than one conducting targeted exploration. No response to our transmissions. Since the emission event, several groups have attempted to send radio transmissions toward 3I Atlas. No response has been detected. If the object were attempting communication, we'd expect some acknowledgement of our attempts to reply. Occam's razor. The simplest explanation that fits the data is usually correct. While the electromagnetic burst is unusual, invoking alien technology multiplies the assumptions we have to make. We'd need to assume extraterrestrial civilizations exist, that they send probes, that one happened to pass through our system, that we happen to be technologically advanced enough to detect it, and that it chose this moment to reveal itself. That's a lot of assumptions. Dr. Alan Stern, principal investigator of the New Horizons mission that flew past Pluto, offered this perspective. Every time we've encountered something unusual in space, from pulsars to fast radio bursts, the initial reaction includes speculation about artificial origins, and every time the eventual explanation has been natural phenomena we simply hadn't encountered before. I expect 3I Atlas will follow the same pattern. The universe is weird enough without invoking aliens. Yet the probe hypothesis refuses to die, precisely because some aspects of 3I Atlas don't fit neatly into our natural categories. And there's a philosophical argument here worth considering. If we reflexively dismiss the possibility of artificial objects every time something unusual appears, might we miss the real thing when it finally arrives? The Fermi paradox asks, if intelligent life is common in the universe, where is everyone? One proposed answer is that we simply haven't recognized the evidence yet. Perhaps interstellar probes disguised as comets pass through regularly, and we've been classifying them as natural objects because we expect natural objects. This is speculative territory, clearly labeled as such. The probe hypothesis for 3I Atlas is not mainstream scientific consensus. It's not what most astronomers believe, but it is being discussed, debated, and investigated by scientists who take the question seriously. Whatever the truth, 3I Atlas has reminded us of an important lesson. The universe is under no obligation to make sense to us on first encounter. Whether this object is an exotic comet exhibiting previously unknown physical phenomena or something more profound, it deserves our serious attention and our best scientific analysis. And it raises the profound question, if this is natural, what are we missing about cometary physics? And if it's not, what comes next? Now I want to take you on a journey into the most dramatic what-if scenarios surrounding 3I Atlas. This is pure speculation, a thought experiment exploring the implications if the probe hypothesis were true. I'm going to remind you constantly, this is not what I believe is happening. This is not what the evidence strongly supports, but it is worth exploring to understand what might be at stake. What if this is artificial? What if it's a probe from an extraterrestrial civilization? And, most unsettling of all, what if the electromagnetic burst near Mars wasn't a greeting? What if it was a warning? Let's build this scenario step by step, grounded in real physics and realistic assumptions about how an encounter with alien technology might unfold. Imagine a civilization orbiting a star dozens, hundreds, or thousands of light-years away. They've achieved technological sophistication far beyond ours, perhaps thousands or millions of years ahead. They've solved the engineering challenges of interstellar travel and launched thousands of self-replicating probes into the galaxy, each tasked with exploring nearby star systems. One of these probes, after a journey lasting tens of thousands of years, enters our solar system. Its artificial intelligence, far more sophisticated than anything we've created, begins its assessment. It scans the sun's spectrum, maps the planetary orbits, analyzes atmospheric compositions, and it detects something unexpected: Earth. A planet with atmospheric oxygen, water vapor, and the spectroscopic signature of industrial pollutants. Clear evidence of technological civilization. The probe's programming includes protocols for dealing with technological species. Perhaps these protocols are benign: gather data, observe, report back to the home civilization, though any such report would take centuries or millennia to arrive. Or perhaps they're more complex, based on the sender's philosophy about other civilizations. The probe's initial assessment: humans have achieved radio technology, space travel, and rudimentary understanding of physics. We're young, potentially dangerous, unpredictable. We've been broadcasting our presence via radio and television signals for only about 100 years, a cosmic eye blink. The probe decides to conduct a test. It will perform a close approach to Mars, where human spacecraft orbit, and emit a structured signal. The purpose? To gauge humanity's response capability. Can they detect artificial signals? Can they interpret mathematical patterns? How quickly do they respond? What technologies do they deploy? This is the emission event of October 23rd. Our response was revealing. We detected the signal within hours. Multiple spacecraft recorded it. Within days, teams of scientists were analyzing the data, recognizing the patterns, understanding that something unusual had occurred. But our response was also chaotic, uncoordinated, and exposed our vulnerabilities. There was no unified human protocol for responding to potential extraterrestrial contact. Different space agencies issued different statements. SETI organizations debated whether to attempt transmission. Amateur radio operators began broadcasting their own messages toward 3i Atlas's projected position. From the probe's perspective, humanity revealed itself as technologically capable of detection, scientifically sophisticated enough to analyze signal structure, but politically fragmented and lacking coordinated response protocols. Now here's where this scenario turns dark. What if the probe's mission includes a defensive component? What if its creators, having encountered aggressive civilizations in their travels, programmed their probes to neutralize potential threats? The structured signal might not have been "hello." It might have been "we see you, we're assessing you." Your response determines what happens next. The mathematical patterns, the prime numbers, the periodic structures, could be a test. A civilization that can interpret these patterns has achieved a threshold of technological sophistication that makes it either a potential partner or a potential threat. And the 47-second duration? Perhaps that was calibrated precisely, long enough for any civilization with Mars-orbiting assets to detect and record, but short enough to avoid provoking immediate panic. Here's the nightmare scenario that keeps a small number of scientists awake at night, though they're hesitant to discuss it publicly. What if 3i Atlas isn't leaving? What if the hyperbolic trajectory we've calculated is exactly what it wants us to believe, but the object has propulsion capabilities that will allow it to alter course once it's beyond easy observation range? What if it's positioned itself to observe humanity's response over the coming months and years, making a final determination about whether we represent a threat to its creators' interests? What if there are more of them, and 3i Atlas is just the scout? In this worst-case scenario, the probe determines that humanity is a rapidly expanding technological civilization that will eventually develop interstellar capability. It assesses us as potentially aggressive based on our own history of conflict, colonization, and resource exploitation. It concludes that the safest course of action is containment or elimination before we become an interstellar threat. How might such a probe neutralize a planetary civilization? It wouldn't need weapons in the conventional sense. With sufficient technology, there are numerous ways to devastate a biosphere without ever firing a shot. Kinetic impactor. The probe could alter its trajectory to impact Earth at relativistic velocities, releasing energy that makes nuclear weapons look like firecrackers. Grey goo scenario. If the probe contains self-replicating nanotechnology, it could release machines that consume Earth's biosphere, converting organic matter into more copies of themselves. Biological weapon. A sufficiently advanced civilization could engineer pathogens specifically designed to target human biology, spreading a plague that we couldn't cure before understanding its artificial nature. Electromagnetic pulse. A carefully positioned detonation of nuclear-scale energy could generate electromagnetic pulses that destroy our technological infrastructure, sending civilization back to pre-industrial conditions. Information. Warfare. If the probe has sophisticated AI, it might infiltrate our information systems, spreading disinformation, triggering conflicts, manipulating financial systems, causing civilization to collapse from within. The most terrifying aspect of this scenario is its asymmetry. We would be facing technology potentially thousands of years more advanced than ours. The gap between our civilization and the probe's creators might be comparable to the gap between contemporary humans and early Homo erectus. Our most sophisticated weapons might be irrelevant against defenses we can't even conceptualize. In this nightmarish scenario, what could we do? Realistically, very little. We have no defensive capability against an interstellar-capable technology. Our most powerful weapons are nuclear missiles that travel at a few kilometers per second and take hours to reach their targets. The probe moves at 34.7 kilometers per second and could be millions or billions of kilometers away before we could launch any response. We couldn't shoot it down, we couldn't communicate our peaceful intentions if it had already decided we were a threat. We couldn't hide. It could undoubtedly detect our radio transmissions, our city lights, our atmospheric signatures from anywhere in the solar system. Our only hope in this scenario would be that the probe's creators built in safeguards, ethical constraints that prevent elimination of sentient species, or at minimum, extensive evaluation periods before any hostile action. But that's hoping for benevolence from beings we don't understand, operating under ethical frameworks we can't comprehend, based on motivations that might be utterly alien to our thinking. Stepping back from the abyss, now let me be absolutely clear. I do not think this scenario is likely. I do not think 3i Atlas is preparing to attack Earth. I do not think we're facing imminent existential danger from extraterrestrial probes. This is a thought experiment, an exploration of what the stakes might be if the most dramatic interpretation of the evidence were correct. It's science fiction grounded in real physics, but it's still science fiction. The reason I've walked you through this scenario isn't to frighten you, it's to illustrate why the 3i Atlas event is being taken so seriously by some members of the scientific community. Because if, and this is a vanishingly small if, there's even a tiny chance that we're encountering artificial technology, the implications are so profound that they demand careful consideration. Dr. Stephen Hawking, before his death, warned about the dangers of attempting to contact extraterrestrial civilizations, noting, "If aliens visit us, the outcome would be much as when Columbus landed in America, which didn't turn out well for the Native Americans." But Hawking also acknowledged that the universe is probably not teeming with aggressive civilizations waiting to destroy us. The distances are too vast, the energy requirements for interstellar warfare too enormous, and the motivations for such warfare unclear. Most scientists believe that any civilization advanced enough for interstellar travel would have outgrown aggressive tendencies, that such technology requires long-term stability, cooperation, and peaceful social organization. Aggressive civilizations might destroy themselves before achieving interstellar capability. So while we've explored the worst case, we must remember Speculation is not prediction, fear is not evidence, and extraordinary claims require extraordinary evidence, which we simply don't have for the hostile probe scenario. But the exercise reminds us of something important. The universe might contain other intelligences, and our eventual encounter with them, if it happens, will be the most significant event in human history. Whether 3i Atlas represents that encounter or simply an exotic natural phenomenon, the question itself demands our serious attention. The mystery of 3i Atlas exists within a much larger context of questions about life, intelligence, and civilization in the universe. To truly understand what might be at stake, we need to explore one of the most profound concepts in astrobiology and cosmology, the Great Filter. The Great Filter is a proposed solution to the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations existing and the complete lack of evidence for them. Physicist Enrico Fermi famously asked, "Where is everybody?" Given the age of the universe, the vast number of stars and planets, and the apparent ease with which life arose on Earth, we should see evidence of other civilizations. Yet we don't. The Great Filter hypothesis, popularized by economist Robin Hanson in the 1990s, suggests there's at least one extremely improbable step in the evolution of intelligent civilizations. This filter is so difficult to pass through that it explains why we don't see the galaxy filled with civilizations. The crucial question is, where is the filter? Is it behind us or ahead of us? If the filter is behind us, somewhere in the progression from non-life to technological civilization, then we're extraordinarily lucky to exist, but the future is relatively open. The hard steps might be the origin of life itself, the evolution of complex cells, the development of multicellular organisms, the emergence of intelligence, or the invention of technology. But if the filter is ahead of us between our current level and becoming a mature interstellar civilization, then we're in potential danger. Something prevents civilizations from spreading across the galaxy, and we haven't encountered it yet. What might a future filter look like? Several possibilities have been proposed. Self-destruction. Civilizations might inevitably develop technologies capable of destroying themselves. Nuclear weapons, engineered pandemics, artificial intelligence gone wrong, nanotechnology disasters, environmental collapse, before they achieve interstellar capability. We might be watching our own species approach this filter with climate change, nuclear proliferation, and rapidly developing AI. Resource limitations. Interstellar travel might simply be too expensive energetically. Even if technologically possible, the resource investment required might be so enormous that no civilization bothers to expand beyond its home system. Technological plateau. There might be fundamental physical limits we haven't discovered yet that make certain technologies impossible, faster than light travel, for instance, or even sustained interstellar travel at sub-light speeds. Existential risk from contact. Perhaps the reason we don't see evidence of other civilizations is that making yourself known in the cosmic neighborhood is dangerous. There might be predatory civilizations that eliminate any potential competitors, or automated systems left by extinct civilizations that continue neutralizing emerging species. This last possibility is what's called the dark forest hypothesis, named after Liu Cixin's science fiction novel. The idea is that the universe is like a dark forest where predators lurk. Any civilization that reveals its presence is taking an enormous risk. The safest strategy is silence and hiding, which would explain why we don't detect anyone. Now here's how 3i Atlas connects to these concepts. If 3i Atlas is natural, it tells us nothing about the Great Filter. It's just an interesting astronomical phenomenon that expands our understanding of cometary physics. But if 3i Atlas is artificial, a probe from another civilization, it provides crucial information about where the filter might be. The filter is behind us. If another civilization exists and has achieved interstellar probe technology, it means at least one species has successfully navigated the entire chain from origin of life through technological development to interstellar capability. This would be extraordinarily encouraging for humanity's long-term prospects. We'd know it's possible to survive the dangers ahead. Multiple filters exist. Perhaps there are multiple difficult steps, and while the probe's creators pass them all, they still might be rare. We might be looking at one of only a handful of successful civilizations in the galaxy. We're being evaluated. If the probe is observing us, we might be approaching our own test. Perhaps the filter for technological civilizations is contact with existing ones. Species that handle contact poorly get eliminated or contained, while those that respond appropriately are welcomed into a larger galactic community. Dr. Andrew Snyder-Beatty, a researcher who has studied the Great Filter extensively, notes, "Every interstellar object we detect is an opportunity to gather data about how common active technological civilizations might be. If we eventually determine that artificial probes are passing through our system, it would revolutionize our understanding of our place in the universe and our assessment of existential risks." The statistical argument is fascinating. If interstellar probes are common, say thousands of civilizations have each sent millions of probes across the galaxy over billions of years, then we'd expect several to pass through our solar system per century. The fact that we've only recently started carefully observing such objects means we might have missed hundreds throughout human history. Or perhaps they're not common at all. Perhaps Three-Eye Atlas is natural, and we're still alone in the galaxy, facing the filter ahead of us with no guidance from species that came before. This raises profound questions about our own trajectory as a civilization. Are we approaching the filter right now? Is climate change our great filter? Is artificial intelligence? Is it something we haven't even identified yet? Perhaps something that only becomes apparent at higher technological levels? Should we be sending our own probes? If the galaxy is indeed a dark forest, advertising our presence might be suicidal. But if it's not, remaining silent might mean missing out on contact with other civilizations and the knowledge they could share. How should we respond to potential evidence of other civilizations? Do we try to communicate? Do we stay silent and observe? Do we prepare defenses against possible threats? The philosopher Nick Bostrom has argued that finding evidence of widespread life in the universe might actually be bad news for humanity. His reasoning, if life commonly arises but we see no evidence of advanced civilizations, it suggests the great filter is ahead of us. The more common life is, the more likely it is that something prevents it from becoming visible at cosmic scales. Conversely, if life is rare and we're among the first civilizations to arise, then the filter is probably behind us and our future is more open. So, in a strange way, finding that we're alone might be the best news we could receive. It would suggest we've already passed the hardest steps and have a legitimate chance of spreading across the stars. But finding evidence of other civilizations, like a probe visiting our system, tells us that at least one species made it through. That's encouraging. Unless that probe's civilization is extinct now, or unless the probe itself represents the filter by eliminating emerging civilizations. The uncertainty is what makes Three-Eye Atlas so significant. It's a data point in a cosmic equation we're still trying to solve. Whether it shifts the probabilities toward we're alone or we're not alone depends on what it actually is. And this raises the profound questions about our cosmic context, our future as a species, and our place in a universe that might be teeming with life or might be nearly empty. Either answer is profound. Either answer changes everything about how we think about our civilization's trajectory and the dangers that might lie ahead. Let's expand our thinking even further into territory that might seem like pure philosophy but has serious scientific proponents. What if the significance of Three-Eye Atlas isn't just about alien probes or exotic physics? What if it's evidence that challenges our understanding of reality itself? I'm talking about the simulation hypothesis and related concepts about the nature of our universe. Bear with me. This might sound wild, but there are legitimate scientists and philosophers who take these ideas seriously. The simulation hypothesis, popularized by philosopher Nick Bostrom in 2003, proposes that we might be living in a computer simulation created by an advanced civilization. Bostrom's argument is statistical. If technological civilizations commonly reach a point where they can create detailed simulations of conscious beings, and if they choose to run such simulations in large numbers, then the vast majority of conscious entities would exist inside simulations rather than in base reality. The math goes like this. One advanced civilization might run billions or trillions of simulations. So if you're a conscious being, you're far more likely to be one of the simulated consciousnesses than one of the tiny number of beings living in base reality. Now, what does this have to do with 3i Atlas? Consider this. If we're in a simulation, the simulators don't need to render the entire universe in full detail all the time. Just like a video game only renders what the player can see, a simulated universe might only compute details when someone is observing them. This is loosely analogous to quantum mechanics, where observation affects physical states. Interstellar objects like 3i Atlas present an interesting challenge for this idea. These objects come from regions of space that have presumably never been observed by simulated conscious beings. When they enter our solar system and we observe them, the simulation needs to generate their properties consistently with physical laws. But here's where it gets interesting. What if the simulation occasionally produces glitches or anomalies when generating new objects from previously unrendered space? What if the electromagnetic burst from 3i Atlas is something like a rendering error? The simulation trying to reconcile multiple possible states of the object and producing an output that doesn't quite fit our physics. Dr. Melvin Vopson, a physicist at the University of Portsmouth, has actually proposed experimental tests for the simulation hypothesis based on information theory. He suggests that physical reality might have an information processing limit, and we might be able to detect this limit in how the universe behaves at quantum scales. The emission from 3i Atlas could theoretically represent an information overflow event, too much computational complexity concentrated in one location, producing observable glitches. Now, before you dismiss this as too far-fetched, consider that some aspects of quantum mechanics already behave in ways that seem consistent with a computed reality, the observer effect. In quantum mechanics, particles exist in superposition, multiple states simultaneously, until observed, at which point they collapse into a definite state. This is eerily similar to how video games don't render details until the player looks at them. The speed of light limit. This could be interpreted as a frame rate limit for the simulation. Information can only propagate so fast because the simulation can only compute so quickly. Quantum entanglement. Particles that are entangled share states instantaneously regardless of distance. This violates our intuitions about locality, but makes sense if the particles are data in the same computer system rather than truly separate physical entities. The Planck length. There seems to be a minimum scale to space itself below which our physics breaks down. This could be the pixel size of simulated reality. I want to be clear, most physicists do not believe we're living in a simulation, and these interpretations of quantum mechanics are not mainstream, but the ideas are out there, being discussed by serious thinkers. The philosopher David Chalmers has argued that even if we are in a simulation, the things we experience are still real in any meaningful sense. The simulation would be our reality, and the physics within it would be the physics that governs our universe. But here's another angle on 3i Atlas. What if it's a test deliberately introduced into the simulation to see how simulated consciousnesses respond to anomalies? Think about it from the simulator's perspective. They've created a universe with conscious beings developing technology and science. One way to test the sophistication of these beings is to introduce anomalies. events that don't quite fit the expected patterns, and observe the response. Do the simulated beings notice the anomaly? Can they measure it accurately? Do they develop new theories to explain it? How do they react emotionally with curiosity, fear, denial? The emission from 3I Atlas, with its precise timing and mathematical structure, could be exactly the kind of test stimulus that sophisticated simulators might use. This interpretation has an advantage over the alien probe hypothesis. It doesn't require us to assume the existence of other biological civilizations. We only need to assume that we're in a simulation run by some entity capable of creating such simulations, which might be post-biological, might be from the far future, might be fundamentally incomprehensible to us. But it also raises disturbing questions. If we're in a simulation, do our choices matter? Are we truly conscious or just sophisticated programs without genuine experience? What are the simulator's intentions toward us? Some philosophers argue that these questions don't change anything practical. Whether we're in a simulation or base reality, we still experience joy and suffering, make choices, build civilizations. The physics we observe still constrain what's possible within our reality. Others suggest that discovering we're in a simulation could be catastrophic for human psychology and civilization. If people believed nothing truly mattered because it was all just a simulation, social cohesion might collapse. There's also the anthropic principle to consider. The universe seems fine-tuned for life with dozens of physical constants that, if slightly different, would make complex chemistry impossible. Why? One explanation is the multiverse. There are countless universes with different physical constants, and we necessarily find ourselves in one compatible with our existence. Another explanation is intelligent design, but a third explanation is that we're in a simulation specifically set up to produce conscious observers. Dr. Rizwan Virk, a computer scientist and author who has written extensively about the simulation hypothesis, suggests if we're in a simulation, interstellar objects might be among the most interesting things to study because they come from regions of the simulation that were previously irrelevant to the observers. Their properties might reveal computational shortcuts or limits that wouldn't be apparent in nearby, well-established objects. Now, I need to emphasize again, this is highly speculative territory. The simulation hypothesis, while intellectually fascinating, is not currently testable in any definitive way. It's philosophy more than science. But 3I Atlas has reminded us that reality can surprise us, the universe can behave in ways we don't expect, and whether the explanation is exotic natural physics, alien technology, simulation glitches, or something even more outlandish that we haven't conceived of yet, we're reminded of how much we don't know. The great physicist Richard Feynman said, "I think I can safely say that nobody understands quantum mechanics." He was highlighting how even our best theories describe reality in ways that seem bizarre and counterintuitive. Maybe the lesson of 3I Atlas is humility. The universe is stranger than we imagine, possibly stranger than we can imagine. Our theories work incredibly well for most purposes, but at the edges, where we encounter unprecedented phenomena, we're reminded that our understanding is incomplete. Whether we're simulated or not, whether we're alone or not, whether 3I Atlas is natural or artificial, these questions point toward a larger truth. We're at the very beginning of humanity's journey of understanding the cosmos. We've learned an enormous amount in the past few centuries of scientific investigation, but the unknowns likely dwarf what we've discovered. And that's actually wonderful. It means there's still mystery in the universe, still discoveries to make, still ways to be surprised and amazed. Let's engage in another thought experiment. Let's assume, just for this chapter, that 3I Atlas is indeed an artificial probe from an extraterrestrial civilization, not because I believe this is true, but because exploring this possibility helps us understand how humanity would respond to such a discovery and exposes gaps in our preparedness. how would our institutions, governments, space agencies, military organizations, scientific communities, religious institutions actually handle confirmed contact with alien technology? The answer is both fascinating and troubling. We're not really prepared. Currently, no comprehensive international protocol exists for responding to confirmed evidence of extraterrestrial technology. There are protocols for responding to potential SETI signals, the post-detection protocols developed by the International Academy of Astronautics, but these are voluntary guidelines, not binding agreements. The post-detection protocols include provisions like independent verification of the signal before announcing discovery, notification of the UN Secretary-General and other international bodies, full disclosure of detection details to the scientific community, no response transmission without international consultation. But these protocols were written for radio signals from distant stars, not for objects physically present in our solar system. The timescales are completely different. A radio signal from a nearby star would take years for any response exchange. An object in our solar system is here now, potentially observable with telescopes, potentially reachable with spacecraft missions. So what would actually happen? Dr. Margaret Race, a biologist who has worked on planetary protection protocols at NASA, suggested in a workshop on this topic. The first challenge would be attribution and verification. Who has the authority to declare that an object is artificial? What level of evidence is required? And once declared, who coordinates the response? In the case of 3i Atlas, we'd likely see multiple teams would independently analyze all available data. Peer review would occur rapidly, with pre-print papers circulating among the astronomical community. Competing interpretations would emerge. Scientists would be deeply divided, with some insisting on the artificial hypothesis and others arguing for natural explanations not yet understood. The debate would be intense and public, conducted partly through academic channels and partly through social media and press releases. Reputations would be at stake. The history of SETI false alarms would make many scientists extremely cautious about endorsing an artificial explanation. Space agencies like NASA, ESA, Roscosmos, and CNSA would coordinate their response, but imperfectly. National interests would complicate cooperation. Some governments might classify certain aspects of the data if they believed it had military or strategic implications. The US government would likely involve multiple agencies: NASA for scientific analysis, the Department of Defense for threat assessment, the State Department for diplomatic considerations, and intelligence agencies for information gathering and analysis. There would be intense debate about public communication. How much information should be shared? How quickly? How do you inform the public about something this significant without causing panic or being accused of a cover-up? Dr. John Rummel, former planetary protection officer at NASA, noted in an interview, "The challenge isn't technical, it's political and social. The scientific community would want full transparency and open data sharing. Military and intelligence communities would want to assess strategic implications before disclosure. Political leaders would worry about public reaction and economic disruption. These conflicting priorities would create tension and delays. The public would learn about 3i Atlas's possible artificial nature through multiple channels simultaneously: official announcements, press leaks, social media speculation, and tabloid sensationalism. Controlling the narrative would be impossible in our interconnected age. Public reactions would vary enormously. Skepticism. Many people would simply not believe it. They'd assume it was a hoax, misinterpretation, or government disinformation. The history of UFO claims and conspiracy theories would make people wary of alien-related announcements. Religious responses. Different faith traditions would interpret the discovery through their theological frameworks. Some would see it as compatible with their beliefs, God creating life throughout the universe. Others might struggle with theological implications. Religious leaders would issue statements ranging from acceptance to denial. Fear and anxiety. some portion of the population would react with fear, worry about invasion, contamination, or unknown threats. Mental health hotlines might see increased call volumes, doomsday predictions would proliferate online, excitement and hope. Others would react with excitement and optimism, the possibility of learning from advanced civilizations, joining a galactic community, accessing new technology and knowledge. Economic disruption, financial markets would react unpredictably. Certain sectors, space technology, defense, telecommunications, might see volatility. Some economists predict short-term market disruptions followed by a new, space-focused economic boom. Social media would explode with discussion, speculation, memes, and misinformation. Distinguishing credible information from speculation would become increasingly difficult. Military and defense organizations worldwide would conduct threat assessments. Does the probe pose immediate danger? Could it be disabled or destroyed if necessary? Are there defensive measures we should implement? Should we attempt communication? Are there others coming? The challenge is that we'd be operating from a position of profound ignorance. We wouldn't know the probe's creators' intentions, capabilities, or locations. We wouldn't know if destroying the probe, assuming we could, might trigger retaliation. We wouldn't know if attempting communication was safe or dangerous. Some military strategists would advocate for a dark forest approach, minimal interaction, maximum caution, avoid revealing more about ourselves than necessary. Others would argue for attempted communication and cooperation. The scientific community would push for a mission to 3i Atlas to study it directly. This would raise enormous challenges. Feasibility. By the time we confirmed artificial nature and launched a mission, 3i Atlas would be far from Earth and rapidly receding. Even our fastest spacecraft would struggle to catch it. New Horizons, which flew past Pluto, took 9 years to travel 3 billion miles. 3i Atlas will be much farther within a few years. International cooperation. Who launches the mission? Who controls the spacecraft? Who has access to the data? Historical tensions between space powers would complicate cooperation, but the magnitude of the discovery might force unprecedented collaboration. Risk assessment. What if approaching the probe triggers defensive responses? What if it's designed to self-destruct if examined? What if contact with it contaminates our spacecraft with unknown technology or biological agents? Technology limitations. Our current propulsion technology is woefully inadequate for rapid interstellar missions. Even reaching an object moving at 34.7 kilometers relative to the Sun would require capabilities at the edge of our current technology. Despite these challenges, the scientific value would be enormous. Direct examination could answer questions about the probe's composition, its power source, its propulsion system, whether it contains any data storage or computational systems, and whether there are any indicators of its origin or purpose. If we confirmed that 3i Atlas is artificial, it would fundamentally reshape human civilization in numerous ways. Scientific revolution. Our understanding of physics, engineering, and the possibilities of technology would be revolutionized. Even without accessing the probe's technology, simply knowing what's possible would redirect research priorities. Philosophical and existential impact. Confirmation that we're not alone in the universe would be the most significant philosophical development in human history. Every worldview, every philosophy, every religion would need to integrate this new reality. Space program priorities. National and international space programs would be dramatically reoriented toward interstellar capability. The resources devoted to space exploration would likely increase by orders of magnitude. Social changes. Human culture would shift in unpredictable ways. Some predict increased global unity, a recognition that we're all humans facing a wider universe together. Others predict increased tribalism, competition for advantage in a cosmic landscape where other civilizations exist. Technological development. the pursuit of technologies capable of interstellar travel would accelerate. Nuclear fusion, antimatter drives, light sails, generation ships, concepts currently on the drawing board, would receive massive investment. Legal and ethical frameworks. We'd need new international laws governing interactions with extraterrestrial artifacts, deciding ownership of any technology recovered, and establishing protocols for future contact. The challenge throughout all these phases would be managing uncertainty. We'd be making decisions with incomplete information, under time pressure, with global stakes, and without historical precedent to guide us. Dr. Stephen Dick, former NASA chief historian and astrobiology chair at the Library of Congress, has written extensively about how society would respond to contact. The greatest challenge would be cognitive, integrating the reality of non-human intelligence into our self-understanding as a species. This isn't just about technology or science, it's about identity, meaning, and humanity's place in the cosmos. One of the most intense debates would be whether to attempt communication with 3i Atlas or whatever sent it. Arguments for attempting communication, opportunity for unprecedented knowledge exchange, demonstration of humanity's peaceful intentions, possible access to advanced technology and science. Joining a larger galactic community, the probe's presence suggests its creators are willing to explore unknown risks from revealing our location and capabilities, potential misunderstanding leading to conflict. The probe might be autonomous and dangerous. We should observe and learn before revealing ourselves. Historical precedent suggests contact between civilizations of different technological levels often goes badly for the less advanced. The debate would likely split along predictable lines, with scientists generally favoring communication and military strategists favoring caution. The public would be divided. Religious communities would have varying perspectives based on their theological frameworks, and here's the frustrating reality: we probably wouldn't reach consensus. Different nations and groups might take different approaches, undermining any unified human response. Our history provides some, albeit imperfect, analogies. The age of exploration. When European civilizations made contact with isolated societies, the results were often catastrophic for the less technologically advanced culture. This history makes many people cautious about contact. The discovery of radioactivity. When we discovered new physics, we both benefited enormously: medical imaging, nuclear power, and created existential threats, nuclear weapons. Contact with advanced technology might follow a similar pattern. The response to COVID-19, our recent pandemic response, shows both humanity's capacity for rapid scientific cooperation and our tendency toward political fragmentation and misinformation. These same strengths and weaknesses would likely appear in response to confirmed extraterrestrial contact. The truth is, we're not as prepared as we should be for something this significant. Our institutions, our protocols, our international cooperation mechanisms, all are optimized for terrestrial challenges, not cosmic ones. But perhaps the most important lesson would be this: if 3i Atlas really is artificial, it means that somewhere, sometime, another intelligence solved the problems we're currently facing. They achieved interstellar capability. They survived long enough to send probes across the galaxy. They navigated whatever challenges we're still approaching. That would be, in its own way, a message of hope. It would mean it's possible, that the great filter, if it exists, can be passed, that civilizations can survive, grow, and expand beyond their homeworlds. Whether that's comforting or terrifying depends on your perspective, but it would fundamentally change the equation for humanity's long-term survival and our place in the universe. There's a fascinating tension at the heart of the 3i Atlas situation that deserves its own exploration: the balance between open scientific inquiry and security concerns, between public transparency and information containment, between satisfying curiosity and managing risk. This tension isn't unique to potential extraterrestrial contact. It appears throughout the history of science and technology, particularly when discoveries have strategic or security implications. But 3i Atlas brings this tension into sharp focus because the stakes are potentially so high and the unknown so vast. Let me take you through the arguments on both sides because this isn't a simple question with obvious answers. The scientific community's default position is radical transparency. Science advances through open sharing of data, peer review, independent verification, and collaborative analysis. Thousands of minds examining a problem from different angles invariably produce better understanding than small groups working in secret. Dr. Jill Tarter, former director of the SETI Institute, has argued consistently for transparency in the search for extraterrestrial intelligence. If we discover evidence of extraterrestrial technology, it belongs to all humanity, not to any single nation or organization. Keeping such information secret would be ethically wrong and practically counterproductive. The arguments for transparency include verification. Only through open data can we achieve independent verification of claims. History is full of scientific mistakes that were caught because other researchers examined the data and found errors. Extraordinary claims about 3i Atlas require extraordinary scrutiny from the global scientific community. Distributed analysis. The electromagnetic signal from 3i Atlas is complex. Hundreds of research groups with different specializations, signal processing, cometary physics, electromagnetic theory, pattern recognition, could each contribute unique insights. Restricting access to a small classified group would limit the quality of analysis. Public right to know. If 3i Atlas represents evidence of extraterrestrial technology, or even just unprecedented natural phenomena, the public has a right to know about it. This information affects humanity's understanding of its place in the universe. It's not the property of governments or elite scientific institutions. Preventing misinformation. Secrecy breeds conspiracy theories. If governments classified 3i Atlas data, the resulting speculation and misinformation would likely be more damaging than transparent disclosure of uncertainties. International cooperation. Major scientific challenges require international cooperation. Climate change, pandemic response, space exploration, these all benefit from open data sharing. Classifying 3i Atlas data would fragment the response and reduce effectiveness. Historical precedent. The discovery of pulsars, gamma-ray bursts, and other exotic astronomical phenomena initially baffled scientists. Some briefly considered artificial origins, but open data sharing led to correct natural explanations. The same process should apply to 3i Atlas. Ethical obligations. Scientists have ethical obligations to share discoveries that advance human knowledge. Keeping data secret violates the fundamental principles of scientific inquiry and public service. These are compelling arguments, and they represent the perspective of most working scientists studying 3i Atlas. But there's another perspective typically held by security and intelligence professionals that deserves serious consideration, even if it makes scientists uncomfortable. The containment arguments include strategic advantage. If 3i Atlas contains recoverable technology or information about extraterrestrial capabilities, the nation or organization that accesses it first might gain enormous strategic advantage. In a competitive international environment, sharing this advantage immediately might not serve national interests. Risk of panic. Public disclosure of potential extraterrestrial contact, particularly if the implications are uncertain or potentially threatening, could trigger social disruption, economic instability, or panic. Careful management of information release might minimize harm. Weaponization. Concerns. Any sufficiently advanced technology is potentially a weapon. If 3i Atlas contains technology or information that could be weaponized, immediate public disclosure might create proliferation risks similar to those we face with nuclear technology. Verification. Before disclosure. Making premature announcements about potential extraterrestrial technology only to later retract them if natural explanations emerge could damage public trust and institutional credibility. Some containment period for thorough verification might be appropriate. Adversary advantages. Detailed technical data about detection methods, signal processing capabilities, and observational assets could provide strategic intelligence to potential adversaries. Some data sanitization might be necessary before public release. Controlled contact. If there's any possibility of communication with 3i Atlas or its creators, having coordinated, thoughtful responses rather than multiple uncoordinated attempts might be safer and more effective. Historical lessons. The Manhattan Project, the discovery of nuclear fission's weapons potential, required secrecy for strategic reasons. Some argue that potentially transformative discoveries about extraterrestrial technology might warrant similar treatment. Dr. Michael Warner, a historian of intelligence agencies, noted, "The tension between scientific transparency and security concerns is genuine and unavoidable. Both perspectives have legitimate concerns. The challenge is finding appropriate balance rather than treating it as an either-or choice." The middle path. Structured transparency. In practice, the response to 3i Atlas has followed a middle path, something like structured transparency with delays. The initial detection and basic orbital parameters were shared immediately with the scientific community and public. This allowed independent verification and prevented accusations of cover-up. The electromagnetic emission data was released more slowly, with preliminary analysis conducted by the detecting institutions before wider distribution. This allowed verification of the signal's reality before unleashing global speculation. The detailed signal processing results, the possible mathematical patterns, the periodicity analysis, the information content estimates, have been released gradually through preprint servers and peer-reviewed publications. This allows scientific debate while avoiding premature conclusions. Some data likely remains classified. Military reconnaissance satellites probably observed 3i Atlas, and their capabilities and observations may not be fully public. This doesn't necessarily imply conspiracy, simply that some observational assets are classified for reasons unrelated to 3i Atlas specifically. One fascinating aspect of the 3i Atlas situation is the role of amateur astronomers and citizen scientists. Unlike classified military observations, amateur astronomers with modest equipment have been tracking 3i Atlas since its discovery. This distributed observation network makes complete secrecy impossible. The amateur astronomy community represents a form of democratic oversight, ensuring that professional scientists and governments cannot completely control information about celestial objects visible to anyone with a telescope. Dr. Pamela Gay, director of CosmoQuest, a citizen science platform, observed, "The era of astronomical discoveries being solely controlled by professional observatories is over. Thousands of amateur astronomers worldwide have the equipment and expertise to track objects like 3i Atlas. This distributed capability ensures a level of transparency whether institutions want it or not. This represents a significant shift in how astronomical discoveries are made and verified. The democratization of observational capability acts as a check against information containment."